Our world absolutely runs on data. But here's the billion-dollar question. How do we learn from all that incredible information without totally giving up our privacy? Well, today we're going to break down a really clever technology that tries to solve that exact problem. So let's just jump right in with a super important question. You've probably heard the term anonymized data tossed around a lot, right? The idea is that if your name's taken off, it's safe. But is it really? Is that enough to truly protect you? Well, it turns out there's a huge flaw in that old school way of thinking. You could almost call it the anonymity myth. Because you see, just stripping away names doesn't actually guarantee your data stays private at all. And it's shockingly easy to see how this myth gets busted. This is a classic example of what's called a differencing attack. So picture this. An attacker knows their friend, let's call him Chandler, is the fifth person in some medical database. First, they ask the database, hey, how many people in the first 4 rows have diabetes? The answer comes back, 2. Then they ask, okay, how about in the first 5 rows? The answer is 3. A little bit of third grade math later, 3 minus 2 is 1, and boom, they've just confirmed Chandler's private medical status without ever seeing his name. So what's the big takeaway here? Even when your name is gone, all it takes is a tiny piece of outside info for someone to pinpoint your specific data and expose it. This is a massive, massive problem for privacy. This exact vulnerability is what pushed researchers to go back to the drawing board. They came up with a completely new way to think about privacy, one that offers a much, much stronger, mathematically provable guarantee. And that brings us to the star of the show, differential privacy. Now, the genius of this isn't about hiding the data itself. It's about putting really smart rules on the questions you can ask the data. The whole point is to make it statistically impossible for anyone looking at the final results to know if your personal info was even in there to begin with. It gives every single person plausible deniability. This quote just nails the core idea. Think about it. Whether you choose to participate in a dataset or you sit it out, the big picture results should look almost exactly the same. Your individual contribution just kind of fades into the background, becoming statistically invisible. Okay, so how on earth is that even possible? It sounds a little like magic. Well, the secret ingredient is something called smart noise. I want you to imagine 2 parallel universes for a second. In universe A, your data about loving coffee is in a database. In universe B, it's not. A differentially private system makes it so that if you ask both databases, how many people here like coffee, the answers you get back are so similar, so close, that you could never tell which universe you're in. That's plausible deniability in action. Now, when we say noise, don't just think of random static on a TV. This is a very precise, carefully measured amount of mathematical noise that gets added to the true answer of any question. It's just enough to hide what any one person contributed, but it's small enough that you can still see the useful overall trends in the data. And how do you control how much noise gets added? That's all governed by one critical little parameter, the Greek letter epsilon. You can think of it as the master privacy dial. Setting this dial is a real balancing act. If you choose a low epsilon, you're cranking up the noise. That gives you incredible privacy protection, but the data gets a bit fuzzier, less accurate. On the other hand, a high epsilon means less noise, so your data is way more accurate, but the privacy guarantee isn't quite as strong. Now, I know this might all sound pretty abstract, like something you'd only hear about in a computer science class. But the crazy thing is, you're already using systems built on differential privacy every single day. I mean, just look at this. The US Census Bureau has been using it for over a decade. And then all the big tech players got on board. Google, Apple, Microsoft. This isn't some experimental new idea. It's become a fundamental tool for any organization that wants to analyze data without compromising user privacy. So what are these companies actually learning with it? They're figuring out broad trends. Apple can see which new emojis are getting popular so they can improve your keyboard. Google can see traffic patterns to make your maps better. Microsoft can spot common software bugs to make Windows more stable. And they do it all without needing to know what emoji you just sent, what route you just drove, or what specific bug crashed your computer. But as powerful as this all is, it's not a magic wand. It comes with a fundamental challenge, a trade-off that everyone, from engineers to you and me, really needs to understand. We're right back at that epsilon dial. The core challenge of differential privacy is this. You just can't have perfect privacy and perfect data accuracy at the same time. It's impossible. As you increase the privacy by adding more noise, the usefulness, what data scientists call the utility, of that data naturally goes down. And it's so important to get this. This trade-off isn't a bug or a flaw in the system. It's a fundamental mathematical law. It means every single company or organization using this technology has to make a very deliberate and sometimes very tough choice about where they want to live on that spectrum. And that really leaves us all with a final, pretty deep question. In a world that's only becoming more and more reliant on data, what is the right balance? How do we decide? There's no single easy answer here, and it's a conversation that's going to be shaping our digital lives for years to come.